Okay, let's start the afternoon session. The first talk will be by Rémi Barlow from Nokia Bell Labs. He will talk to us about quantum something.
Yeah, quantum 2.0, so second quantum revolution, and the activities it links. There's a few parts to my presentation. Quantum 2.0, what that is, because even though quantum has been getting a bit of attention lately, a lot of people still don't really know what we're talking about. Once that's out of the way, talking about the different activities at links we have around quantum, as well as the different research that we're doing. And I will finish with a shallow deep dive of my own activities on quantum networks. With that out of the way, why quantum 2.0? Because we're talking about the second quantum revolution. So to understand, we first need to go back to what was the first quantum revolution when we started understanding quantum physics and what we could build with it. And this was quite a while back, and it brought us a lot of inventions. The idea was to look at the statistical properties of quantum particles and see what we could build with them. And this brought us things like the transistor, lasers, GPS, photovoltaic cells. All of these relied on our understanding of quantum physics applied to ensembles of quantum particles. The second quantum revolution is moving to individual quantum particles. What happens when you look at individual photons and their properties, individual atoms and the like? And this is what all the recent hype is about. And there are here, again, a number of applications that you may or may not be aware of. The most famous one being quantum computers. So quantum computers are interesting for a lot of reasons. And for the links, there are a lot of applications to networking in general, in communications. The second most famous quantum algorithm, Grover's algorithm, basically tells us that things like the traveling salesman problem or bin packing problem, all of which have huge applications for networks and communications, can all be sped up using quantum algorithms. So this is an important domain when looking at these applications. Second obvious one is quantum networks. Obviously, if you're doing networks, looking at how quantum networks operate, what they do, and what they bring to the table is essential. I'll come back to that later in the talk. Quantum security. So the most famous quantum algorithm probably is Shor's algorithm, which breaks RSA, simply put. And so there's the question of what do we do to adapt to that, both classically with something called post-quantum cryptography, but also using quantum approaches to actually improve security. So we have quantum key distribution, but we also have quantum network certification or distributed quantum algorithms around consensus, which provide new tools for security. And finally, quantum sensors. This is a broad range of applications where we really look at what quantum physics can bring. Typical examples are the ability to build chips which are so fine in their evaluation of the magnetic and gravitational fields that we can have very specific location, like centimeter level or below, without relying on GPS. We can know with these chips where we are on Earth at that level of precision without relying on anything external. Similarly, if you want to map radio frequencies around you and have sort of the spectral representation of the radio environment, today this requires huge setups. With quantum sensors, we could imagine 1 centimeter chips that can give you that information really precisely, and you can optimize from there. That's the second quantum revolution and all the potential applications. Let's look at what's happening at LINX. So at LINX, we've been looking at quantum in general for quite a while. We've had seminars since 2022, already 2 last years and 1 this year, either from people within the LINX. So Ludovic has given a few, or from outside. The last 2 were from people working at INRIA, with whom we were working, Marc-Olivier Renou and Isadora Verine. And then we also have reading and working groups within the LINX, where we have different presentations, and those have been going on since 2019. So we generally have about 2 presentations a year, 1 or 2. to bring quantum back to the front, remind people it exists, and explain. The LINX ecosystem has also given us access to a lot of researchers outside the LINX, but within the affiliated institutions. So thanks to the LINX, we've been speaking with people at INRIA, so the FICUS team, with whom we have already one PhD and a second one coming up. Also Harold Oliver from Quat. Nokia, we have a few people. Amir Hossein working on CVQKD, so continuous variable quantum key distribution, and René Jean Enciamp working on quantum communications. He managed to pack 12.5 bits of classical data into one single photon. So if you're looking at how to reduce the energy footprint of communications, he's somebody you want to talk to. Institut Mines Télécom has a chair team with INRIA, right next to the LINX with INFRES, where Romain Liam and Peter Brown are working on continuous variable QKD as well. We've also spoken with Yves Jaouin more on the hardware side. And we've been able to actually do some teaching at Télécom Sud Paris regarding quantum networks, sort of showcase what we're doing. Systemix, we were able to do presentations at their Critics event for the last 2 years, so more security oriented. Sorbonne, we've been speaking with people at the LIPSIS from the quantum information team, Frédéric Grosson and Émile Diamanti. And then we've also had access to quite a number of startups around Paris and Massy. WeLink working on quantum memories for quantum networks. The others are more looking at quantum computing or quantum data centers, all very interesting people. So that's the global vision. What about the specific research here at LINX? There are really two projects, I would say. The first one is quantum algorithms with Joaquin and Ian, who have been working on that for quite a while. Ian is actually starting his PhD soon, October, I believe, at LINX, but has been working with Joaquin for a while. And so they're looking at algorithms, quantum algorithms, namely applied to networks. Ian has a poster outside, so after this, go and check it out. And he has a presentation, a 3-minute presentation tomorrow, I believe. That's quantum algorithms, and then quantum networks. So this is Ludovic, myself, and Louis, who started a PhD this year at LINX as well, where we are looking at quantum networks and have been working on that for a bit now with a bunch of publications. I will get to that in a minute. We also have a second PhD student starting later this year. Regarding Louis, he also has a poster, so go check that out as well. And he also has a 3-minute presentation tomorrow. Be sure to be there. So that's the global view of what's happening at LINX. Now I get to talk about my own research for a bit. Quantum networks. So to talk about quantum networks, first I have to go through a bit of quantum fundamentals, because I don't think everybody here knows what a qubit is. And even if you do, you may be happy to have a refresher course. So when we look at qubits, we generally compare them to classical bits, saying a classical bit is a 0 or a 1 in memory, and a qubit is a 0 and a 1, whatever that means. So a classical bit, for example, could be 0, but a qubit could be something in between 0 and 1. So you can think of it as a weighted average between 0 and 1, where you're more or less of either value. The problem with qubits is that state, you don't have access to it. We call this superposition, and the values, 75%, 25% I have up there, you don't have access to them. The state of the qubit itself is unknown, and what you can do is something called measurement. You can measure the qubit. That basically means sampling from that distribution. The problem is you're only allowed to sample once. So you get 0 and 1. You never know if it was 75-25 or if it was 50-50. This is the hard part. There is part of that state, part of the qubit, that you will never have access to. You have to live with it. Coming back to the state of the qubit itself, I present it here as a distribution over 0 and 1. It's actually something a little more complicated. If you want to think about a qubit, what it really is, it's a point on a sphere. The point at the top represents 0, so if that's the state, every time I measure it, I would get 0. Well, I get to measure it once, but I'm sure to get 0. If the point is at the bottom of the sphere, I get to measure it once and I'm sure to get 1. And then if I'm elsewhere, the closer I am to the top, the more likely I am to get 0. The closer I am to the bottom, the more likely I am to get 1. I won't use that representation. I'll keep it to the distribution with percentages, but keep in mind that there is a complex state behind that. It's more than just that distribution. And that's what makes it interesting to work with. For quantum networks, we don't necessarily need to go into that level of detail to understand it, so I'll keep it at distribution level. Now, this in and of itself is interesting, but the more interesting aspect, what really brings out the power of qubits and quantum technologies, is what happens when you look at a 2-bit registry. So if you look at this in classical bits, you have 4 possible states, right? And at any moment, your 2-bit registry is in one of those 4 states. So for example, 0, 1. If you look at this in quantum, what you have, again, 4 possible states, but you're going to have a superposition. So you're going to have a distribution over those 4 possible states. And this is where it gets a little tricky. If you look at that distribution and you ask yourself, what's the probability that the first bit is 1? That's the probability of being on the bottom line. That's 0.7. If you look at the probability that the second bit is 0, that's the probability of it being on the first column. That's 0.2. But the probability of having 1 0 is 0, not the product. So what we're saying is, if I measure those 2 bits, the probability of getting 1 0 isn't the probability of getting 1 on the first and 0 on the second. We don't have independence. There is a joint distribution here, or to put it differently, we have something called entanglement, where the state of the quantum registry cannot be expressed as the state of the individual qubits. If you have a classical registry, if I tell you what is in each cell, you know the state of the registry. In quantum, that's not the case. If I give you the marginal distribution for each qubit, you do not know the state of the registry. You need the joint distribution. This is something we can't replicate classically. This is very different, and this is very powerful. Just to give an example, one of the most common entangled states that we use, and that is very useful in quantum networks, is something we call the Bell states. So there are 4 of them. 2 of them, phi plus and phi minus, are such that we have a 50-50% chance of having either 0, 0 or 1, 1. So why are there 2 with only 1 distribution? Because again, the state itself is more complex than that distribution. So it's 2 very distinct states that just happen to give the same distribution. What's important to notice is if I measure the first qubit and get a 0, then I am guaranteed that when I measure the second qubit, I will get a 0. And if I measure a 1, I'm guaranteed that measuring the second qubit, I will get a 1. So measuring 1 qubit fully reveals what will happen when I measure the second qubit. But until I've measured the first qubit, the distribution of the second qubit is completely random, right? 50-50. And the other 2 Bell states is the same thing. The distribution is this time 50% on 0, 1 or 1, 0. But if I measure 1 qubit, I know exactly what will happen when I measure the other. So we say they're fully entangled. So these 4 Bell states are central to what we're going to do. One of the most common applications for Bell states is quantum key distribution. If I take those 2 qubits in the registry, bring them apart and have 2 people measure them, if it's one of the phi states, I know they will have the same exact measurement. Do that again and again with different Bell states, and you create a shared secret. And for reasons I won't get into, you have the guarantee that nobody else has access to that shared secret. You're capable of distributing a key in the network in a completely secure fashion with a guarantee that people have the same key on either ends. So now that we have these quantum fundamentals out of the way, let's look at quantum networks and what the problem with them is. So a quantum network is still a network. You have nodes and links. And the aim of the quantum network, the one thing you're trying to achieve, is distributing entanglement. you want to do what I just explained in the previous slide. Take two entangled qubits, a Bell state, and move those two qubits to the end of the network, one qubit to each side. So for that, sorry, that's what I just said. For that, we have one piece of equipment that works, and these we actually have today, which are Bell state generators, we'll call them. Basically, hardware that is capable of emitting two photons that are entangled in a Bell state. That we have. And from there, you would imagine that it's simply have one in the middle, and then you send qubits left and right till the endpoints, and you route them all the way. That would be the intuitive approach. The problem is that doesn't work. The reason that doesn't work is because we're sending individual photons, and the survival rate of an individual photon in fiber is not that great. Basically, you lose 9 out of 10 every 50 kilometers. That's 1 in a million after 300 kilometers, and after, say, 1,000 kilometers, you have nobody left. So we can't take that direction. And while we're at it, it's also important to note that we cannot repeat or amplify the signal. When you do that with classical networks, you're measuring what's coming in to re-emit it. Here, if we measure qubits, as I stated earlier, we don't get the full state. We only sample from the distribution. And that's not what we're trying to send. We're trying to actually send the full state. So we need to play around a bit and find solutions for this. And the solution is a bit complex, so bear with me. Well, a bit. What we're going to do is we're going to generate entanglement along each link, along 50 kilometers. And we'll have 90% loss, and we'll live with it. That's something which, as distances increase, will not change because we'll just add routers, but the link size will stay roughly the same. And then in each quantum node, we're going to have quantum memories. So we emit qubits, and we store them in the quantum memories. Of course, some of those qubits are lost. So here you can see I have empty spaces in memory where there was no inbound qubit. And then what we do is we acknowledge what was properly received. The two memories say, this is what I received, this is what I didn't receive. And we get rid of whatever was not received properly by the other side. If I've received a photon, but the other node didn't receive their photon, my photon is completely useless. I might as well get rid of it. Yeah. I'm storing them. I'm storing the qubit. I need to know I received the photon. So this is an important question. Yeah. This is something we call the heralded transmission. I'm capable of determining I received the photon without measuring it. A photon is more than just the quantum state encoded inside of it. Does that answer the question? Yeah. No, it's. So once we've got that acknowledgement, we've gotten rid of the qubits that were not paired with something received on the other side. Then we end up with some qubits left, and those qubits we know are entangled with a qubit on the other side. We're going to do this along every link, and you can do this in parallel throughout the network. Every link can do this at the same time. This is very different from what we're used to in classical networks, where there's this sort of progression. Here, this is a completely distributed asynchronous process. Once we get there, we attack part 2 of the plan. So focusing just on one node for now, I'm going to look at the middle node. We do a quantum operation called Bell state Bell state measurement, sorry. And what Bell state measurement does is take a photon, so a properly paired photon from each side, and stitch the entanglement together. Basically, I'm going to destroy the two local photons. Well, they're not photons anymore, but the two local qubits. And destroying those two qubits in a certain way, I'm going to ensure that the two remote corresponding qubits are now properly entangled in a Bell state. You do this, again, in parallel, asynchronously in each router, and you obtain end-to-end entanglement. There are two caveats here. First one, kind of obvious, is that if I'm Alice, I have no clue at this moment who I'm paired with, right? I had the purple qubit, but who does it correspond to on Bob's side? The second caveat is that when I do Bell state measurement, I say the two remote qubits are now in a Bell state. If you remember correctly, there are 4 Bell states, and which one they are in is selected completely at random. The good news is whoever in the middle did the Bell state measurement knows which one it is. The two remote nodes do not and have no way of knowing. So from here, if we actually want to be able to use this, each node in the network has to send two pieces of information to both ends. Who was paired with who during the stitching phase, and what were the measurement results for the Bell state measurements, which tell you what the actual Bell state is from end to end. And once you've sent these two informations to both ends, you can use that Bell state properly to do lots of things with it. You can measure it for quantum key distribution. You can use it to transmit quantum states with something called quantum teleportation. Basically, if I have a qubit here that I want to send, and this qubit that's paired with the one over there, I can do a Bell state measurement again here, some work over here, and now the qubit I wanted to send is over there without ever moving through the network. Yeah. So there's, as I said here, this communication here at the bottom is using classical network. Yes, that's important. One of the key aspects. Yes and no. Okay. Yeah, but I mean, with quantum networks, you have such errors that the errors in the classical network are not your problem, honestly. But there is a question. The security question is important. Here, the bits of information I'm sending, I can send them publicly. I don't need to encrypt them, and there is nonetheless no security threat in that regard, because they will not allow anybody to actually intercept that Bell state. It's a bit tricky, but if somebody tries to intercept the qubits themselves, they will destroy it, and you can detect it between Alice and Bob. If you don't destroy it, if you don't grab that, then whatever is happening here, the information you're sending is useless. Think about it. As I said, when you do the Bell state measurement, you find out, you actually get 2 bits, classical bits of information, which tell you what state the 2 remote qubits are in. They are 2 completely random bits. They are noise from a news. You have noise. You have random bits. The classical bits that are sent are completely random noise. The qubits that were sent prior to that, you could not intercept.
Given state between but that's not information, just a correlation. Then the usage you will do it after for Tucali or quantum distribution or quantum teleportation, and you do not have any information.
So the Bell state measurement is the thing that does the stitching. It stitches the 2 Bell states. Yeah, Bell state measurement, sorry, is this operation here that does the stitching. It's not what we do here or here. Yeah. Is the central operation. Sorry, yes. So once you're here, yes, this is the function of quantum networks. This is how they work. This is everything you have to do. And our work with Ludovic focuses first on creating a full quantum protocol stack. There is a lot of information you need to move around, from the measurement results to who you stitch with who, to later resource reservation, assigning, routing in a sense. Here I just showed a path, but once you do routing, there's a lot of metadata going around in the classical network to make this quantum network work. That requires its own protocol stack, and that's what we're designing today. For that, we have actually built an in-house quantum network stack simulator, protocol simulator. We also have 2 PhDs who are looking more at the applications for quantum networks. So what can we do with a quantum network? Louis is working on network certification, trying to see how we can check that the network is operating properly. And our upcoming PhD will be looking more at quantum Byzantine problems. Finally, a lot of education and awareness. Every time I present quantum networks, I have to start with what are quantum technologies, what we can do with them. And every time I have one more person in the audience who knows what's happening and who remembers. But yeah, it's still sort of a dark area for a lot of people. And we are constantly working on making sure people understand what's happening because there's a lot of potential. There's a lot of potential for theoretical studies. We have quantum computing theory, quantum network calculus, things like that are coming up, where we feel there's a lot of potential. People are just not aware. That's all I have.
Any question? Yes.
It's a general question. So, it's a long. So people talk about quantum computing and networks.
Yep.
Since like much time ago, like 70s maybe or something. So why now it's the right moment? Because it feels now more people are getting into this and there are startups, etc. So what's happening? Why now there is this revival?
So the quantum computing part, the algorithms have been studied for a while. What was really lagging and the reason we couldn't really do anything with it was hardware. And this is true similar to AI. There were a lot of AI algorithms which were very old in machine learning where nothing was happening because we just couldn't run them. And then when we started having the hardware to run them, ML became everything. Quantum, it's kind of the same thing. We are seeing concepts, hardware concepts that are showcasing that, wait, this is coming. In computers, we have the IBM, Microsoft, and the like that are doing things. But we also have in networks, quantum key distribution. We have currently commercial products that exist, which allow you to run quantum key distribution over 100 kilometers. We don't have the quantum nodes that I had here yet, the quantum routers, because that memory is missing. But WeLink, the startup that we've been in contact with in Paris, who's working on quantum nodes, starting to have a proof of concept of quantum memories that would work for quantum networks. So the reason we're looking at it at the software side, algorithm side, I'll say, is because the hardware is catching up.